In this tutorial, we're going to discuss the use of floating point variables with the Omron CJ2M PLC. To demonstrate this, we're going to use a sample problem. The problem could have come in from a client, in this case a pizza manufacturer, who requires a new interface to allow the user to set the diameter of a pizza in order to calculate the volume of dough with the answer given in centimeters cubed. So that's part one of this particular problem. Part two of the problem, once the volume has been calculated, a stepper motor will pump 1 centimeter cubed of dough per revolution. For that, we need to use the high-speed timer in order to create a signal to run the stepper motor, or to run the stepper motor driver. We're not using a particular driver card for this, it's just to demonstrate the use of a high-speed timer. We'll cover that in a different video. The third part of this particular problem, once the stepper motor has completed, the user should be informed through the HMI that the process is finished and bring me back to this first screen. Again, we're going to deal with this in a separate video about using multiple screens and moving between the different screens within the HMI. Why do we need to use a floating point in this particular case is because we don't necessarily have even numbers, for instance pi. So in order to work out the volume, we need pi to be equal to 3.141529. So let's look at what we have available. These are the set of basic data types available with our PLC. We start with bool, which is a binary value, 1 or 0, so we can't use that to store numbers. We have an integer, which has got a size of 16 bits. In that case, we can go minus 32,768 and plus 32,767. So we can't store a number in there either. We've got a dint, which is double size integer, which gives me 32 bits. We've got a long int, which is a 64-bit number, we've got a uint. This is a particular type of an int. So it's the same as the int here, except it's unsigned. So that gives us a range between 0 and 65,535. Just note the AND sign in front of that for later. We have an unsigned d integer, which is 32, which is an unsigned double, and then we have an unsigned long int. We also have a real and a long real, a word, a d word, and an l word. So the one we're interested here is going to be the real number. A real number being a number with a fraction or a point afterwards. So in this case, if we want to store our pi, which is 3.141592, we can store that within a real number. The long real is a real number but with 64 bits. We're going to go through these in a separate video in a lot more detail when we cover counters and timers, but for now we'll just leave them aside. All we're really interested for this video is real numbers, booleans, and possibly ints. So to do this, we need to use a particular set of functions. Again, in a different video I've covered how the move function works, and I'll cover it again later on as we're programming this code. But for a floating point, we're going to use move f. If we want to use a floating point, convert a 32-bit floating point value to a 16-bit signed binary value, we need to use this function. So these functions are all available and all detailed within the data. So there's a whole set of functions for just dealing with floating points. The ones that we're most interested in for this particular example are going to be plus, minus, multiplication, and divide. The only difference between them and multiplying two integers is just that you have to put the f in to indicate that you're trying to plus, minus, divide, or multiply a float. And again, just remember that we have our option here, which is the @ sign, which is for a differential. So what are we trying to do? Well, in order to work out how much volume we need for a particular pizza, I've picked this nice looking deep dish here. We need to know a few different variables. We need to know the radius, we need to square it, and we need to know the height in order to work out the volume. This was taken from Google and it allows you to type in the radius and the height, and we'll be using this later to check our answer. So what variables do we need? Well, first of all, we need to know the pizza size and the radius, and that's going to be a real number. We need to know the height, that's going to be a real number. We're going to need to square the radius, so it's going to be a squared radius. And finally, we need the volume. We also need to know what pi is, but this is not a variable, this is going to be a constant. And later on, when we're looking at the HMI, we're going to need this HMI value. So a real number, I'm putting in memory address D1 for data memory. This is a particular memory space that's used to read and write data values. I've covered that in another video on the memory spaces available within the Omron PLC, including the working area, which is why we have a W here, and the data area, which is why we have a D. Now what's important to note here is that I've given this memory address D1, but I put the height into D3. The reason for that, if I come back up here, is I'm told here that I need 32 bits of space in order to store a real number. But each word only stores 16. So a word being one piece of memory within our PLC. This can differ across different platforms, but in this particular case, our word size is 16. So in order to store a real number, I need to allocate D1, and D2 will automatically be allocated to that in order to fill the entire space for a real value. Again, height is D3, so D4 is given over to that real value, and D5 and D6 will be given up to the squared radius, and the volume will be D7 and D8, with pi being D9 and D10. If you decide to assign height to D2, for example, you will be overwriting the value that's part of pizza size radius, which is part of D2. The important thing to remember here is that the PLC will let you do this and will not complain. It assumes you know what you're doing. So let's get started, and the first thing we're going to do, as always, I suggest, is have our user manual open and available with all the different functions that I can use. So there's your entire user manual, 670 pages, and it tells me everything I need to know about running the PLC. So what we're interested in are the appendices, where we can look at some of the functions that are available for us when we want to use our PLC, including things like if not, timers, counters, to use a loop, all available here and all functions we can use. So let's get started. So the first thing we're going to do is open CX Programmer, and we'll get the PLC software set up first. So File and New, and I'm going to select my PLC type, which as always is CJ2M, and I'm going to select Ethernet IP. For the Ethernet IP address, I'm going to select 192.168.1.1 and enter. So this will create an empty ladder logic program for me, and I have my symbols and I have my section. The first thing we'll do is set up the symbol library. So the symbols I need are going to be pizza size, and that's going to be a real. And I also need height, squared, volume, and pi. So let's start. I'll put my first one in. So the pizza size radius, and that needs to be a real. So from my drop down list here, I'm going to select a real. And I'm going to put that into D1. The next one I need is the height. And that's going to be real as well. And I'm going to put that into D3. Okay, now once I have my height, I need to store my squared radius. So I'm going to create another one here. I'm going to call it squared radius. That's going to be real again. And I'm going to put that into D5. Then we have an output, or what I'm looking for here, which is the volume. And that's going to be real as well. And that's going to go into D7. Now let's put in my constant, which is going to be pi. Okay, so that's everything set up so far in order for me to calculate the volume of my pizza. But how do I actually set the constant value pi? So that's the first thing we're going to do. So if I go over the section, and on my first line of my section, I'm going to put in a contact, and I'm going to use a special variable called p underscore first cycle. So p underscore first cycle is a variable that's set up by default, and it only runs the first time the PLC starts up, or the first cycle. And this is a great way to set variables. So to set a variable, I'm going to come along and I'm going to select over here, which is the new PLC instruction, and I'm going to drop it down here, and the instruction I need was move F space and what I'm going to move from and where I'm going to place it. So the value I'm going to move is going to be plus 3.14. Let me go back to my page. .141592. Okay, it's important here you put the plus in front of this. Where are we going to put it? So a space again, and I'm going to put that into pi. And enter. So now I've moved the float value 3.141592 into the value pi. So that will be set up on the first time that the system starts. I can change the value of pi again, and it will reset back to 3.14 when I restart the system. Okay, so that's my variable set up. Now I need to actually do some code. So for now, I'm just going to set up a holding work bit called work bit 0.01, and I'm just going to use that in this example. So let's look at my formula again. So it's pi times r squared times h. So my first instruction is going to be to find this r squared. I'm going to add a new instruction, and the instruction will be at for the differential multiplied by a float, and the first thing I'm going to multiply is pizza size radius by pizza size radius. I need to output that into a new variable called size radius, or SQ, squared radius, SQU radius. and OK. So there you go. I've now got my SQU radius worked out. The next thing I need to do is I need to multiply pi by it, and I need to multiply h by the result. And this time I'm going to use another instruction, and this time I'm going to multiply squared radius by pi. So I'm adding my instruction down here, and again it's at multiplied by f by squared radius multiplied by pi. In this case, I'm going to put the result into volume, even though it's not quite the volume yet. Okay, so far we have got our pi now multiplied by our r squared, and we're saying that that's equal to volume. I need to multiply it by h in order to work out the volume. Again, I'm going to add another instruction, at multiplied float, and in this case I'm going to multiply the height, which I've given here, height, and I'm going to multiply that by volume, which is where I've stored this value. And I'm going to put the output of that back into the same variable, volume. So I'm effectively just updating the variable volume. And I'm going to click OK. So now we've got all three of these done. So when I select this working bit, the radius will be multiplied by the radius to square it. The square will then be multiplied by pi, and that will be put into this. We'll put that into volume. We'll then multiply the height by the result, which in this case is stored in volume, and we're going to output that back into the same variable, which is volume. So let's test our code. To do that, I'm going to use simulation, and I'm going to simulate with using work online simulation. You can see here that straight away the first cycle has run, and the value listed for pi is plus 3.141592. Brilliant. The squared value is 0, and the squared value multiplied by that, and the answer is currently 0. So we've actually got no values for our height or for our radius. So just to test our code, I'm going to manually add some values. So first of all, I'm going to add a radius, and I'm going to put that in at 10. And I'm going to go set. So now I've set that value to 10. And I'm going to put in a height, and in this case I'm going to put in a height of 5. And I'm going to set that value. So now we've set a height, and we've set a radius. We've no square values yet, because we haven't run the code, and we've no volume yet, because we haven't run the code. So let's run the code. To do that, I'm going to come all the way up, and I'm going to select this work bit that I set up earlier, and I'm going to right click and come down to set. We have two options here. We can use a force, or we can use a set. If I force this value on, it will stay on regardless if someone tries to reset it later on in the code. If I use a set, it will only be set on for this amount of time. So let's set it on, and you can see now that the value has been set, and let's set it off. So now you can see here now that we have a squared value of 100, and when the height is multiplied by the volume, we have a value of 1570.496. Let's test this and see if our code has worked. To do that, I'm going to use the trusty Google and type volume of a cylinder. So the values I picked were 10 and 5. And we get 1570.8, and our answer from our code was 1570.796. So it looks like we've worked out the volume correctly. In the next part of this video, we're going to look at the HMI and how we can configure the HMI to work with this code.